we'll go ahead and actually just go through the do now together. So there's two kind of short answer type questions, and then there are two multiple choice questions. So we're going to look at all of them, and we'll focus on how to tell how to solve a problem. Because now we've covered all types of gases. We've looked at the combined gas law. We've looked at the ideal gas law, partial pressures, stoic, diffusion and effusion. So we'll take just a few minutes to actually look at each question and how we know what to solve. So for number one, it says that a tank contains both HCl and HI and it develops a leak. What is the ratio of the rate of effusion of HCl to HI? So this problem is telling us that we're looking for rate of effusion. So looking at rate of effusion is looking at Graham's law. Okay, so Graham's law of effusion says that the rate of effusion of a gas is inversely proportional to the square root of the molar mass. So Graham's law looks like this. The rate of gas 1 over the rate of gas 2 is inversely proportional. That means that the fractions get switched, but it's inversely proportional to the square root of the molar masses. So since it's inversely proportional, if gas 1 is on the top on one side, it's on the bottom on the other. So if we look at what this problem is really asking for, it wants the ratio of the rate of effusion of HCl to HI. So it wants me to just solve for a ratio. A ratio is nothing more than a fraction. So I want the rate of HCl to HI, which means I want rate of HCl over rate of HI. Just based on the wording of the problem, it wants the rate of HCl to HI. So this is what our ratio will look like, which means HCl is on the top on this side. So the molar mass of HCl will be on the bottom when we look at molar masses. And HI is gas 2. So the molar mass of HI will be on the top. Because they're the same units, they're both molar masses, you do not have to do any conversions. So if we look at calculating the molar mass of HI, look at the periodic table, hydrogen is 1.008, iodine is 126.91. The molar mass of HI is 127.918 grams per mole. So just find the molar masses. Graham's law of effusion is related to the square root of the molar masses. So HCl 1.008 plus 35.45 36.458 grams per mole. This is why you don't have to do any conversions, because it's grams per mole on the top, grams per mole on the bottom. They cancel out. Because the ratio is just a number. There's no units for the ratio. It's a fraction. It's just a number. So I'm going to do 127.918 divided by 36.458. I get 3.509 inside the square root. I take the square root of that answer. And what I get is rate of HCl over rate of HI equals 1.87. Here's what this means. Think about how a number works, right? If I do 1.87, 1.87 as a fraction is 1.87 over 1. So the ratio of the rate of effusion, you can say, is 1.87 to 1. This means rate of HCl is 1.87, rate of HI is 1. HCl effuses 1.87 times faster than HI, which should make sense because remember that diffusion and effusion is based on molar mass. The lighter the gas, the faster it's going to move. The heavier the gas, the slower it's going to move. And so this is our answer. You don't have to have over 1, but it helps people to think about how ratios work as fractions. HCl effuses 1.87 times faster than HI. So that's just looking at Graham's law. Again, Graham's law of effusion says that the rates of effusion are inversely proportional to the square root of the molar masses. Number 2, average kinetic energy is only based on one variable. And what is that one variable? Temperature. Average kinetic energy is based on temperature. That's it. When you see a question that asks you about average kinetic energy, look at the temperature. I ask questions on average kinetic energy every year on the test. Look at the temperature when you're looking at average kinetic energy. If the temperature stays the same, average kinetic energy stays the same. No matter what happens to pressure or to volume or to number of moles, average kinetic energy is only based on temperature. So then 3 and 4, we get into some multiple choice questions, and you can tell that these are sample AP questions because the font is clearly changed, because I just took screenshots of these. So for number 3, a 7-liter container will hold about 12 grams of which of the following gases at 0 degrees Celsius and 1 atm. So when you're looking at identifying a gas, if you want to identify a gas, calculate the molar mass. So again, if you want to identify any gas, calculate the molar mass. With every gas, every one that they're going to give you is going to have a different molar mass. So if you can calculate the molar mass, you can identify what the unknown gas would be. So if you look at what we have volume, mass, temperature, and pressure. There's 2 ways that you can actually go about solving this. I'm going to solve it how I think most people probably will. Well, you have pressure, you have temperature, volume. So it looks like we're going to use a derivation of the ideal gas law. Well, if you remember the molar mass derivation of the ideal gas law, molar mass is dRT over P. To calculate the molar mass of a gas, dRT divided by P. So density, R is the gas law constant, T is temperature, always has to be in Kelvin, P is pressure. Density is always mass per volume. Density of gases is always grams per liter. So I have grams, I have 12 grams, 7-liter container. Make sure that your R value matches the pressure. Since pressure is in ATM, we need to use 0.08206. 0 degrees Celsius is how many Kelvin? 273. And remember, if you forget the conversion, it's on your equation sheet. And then 1 atm. So you have density, 12 divided by 7, times 0.08206, times 273, divided by 1, is 38.4 grams per mole. Once you know the molar mass, just do some quick calculations of these molar masses over here. Chlorine is 19. So we have 38, 71, roughly 160, 28, 16. I know that I didn't go out to all of your, sig figs. I just did quick times 2. So which one of these gases has a molar mass closest to the one that we calculated? A. When you want to identify a gas, calculate its molar mass. It's the best way to identify an unknown. And then number 4, a 0.33 mole sample of calcium carbonate, which is a solid, is placed in a 1 liter evacuated flask, which is then sealed and heated. The calcium carbonate decomposes completely according to the balanced equation below. The total pressure in the flask measured at 300 Kelvin is closest to which of the following? And then they tell you to use 0.082 for R. So here's what we need to think about first. We have 0.33 moles of a solid that is put into a flask. It wants us to calculate pressure. So we know we're going to be finding total pressure. We need to stop and think first. There's only one state of matter that affects pressure. What's the one state of matter that affects pressure? Gases. So the only thing that will affect pressure is CO2. Calcium carbonate, not going to affect pressure, it's a solid. Calcium oxide, not going to affect pressure, it's a solid. So if you're calculating pressure, and look at what you're given, volume, temperature, R is kind of a big giveaway here. Use the ideal gas law. You're solving for pressure. The only pressure that you are solving for in this container is CO2. Gases, this is the ideal gas law. It's not the ideal solid law. So that means that we need moles of CO2 times R times T divided by volume. Now you maybe look at this and you're like, well, they gave me moles of calcium carbonate. Look at your ratio. 1 to 1. And it says it decomposes completely. 1 to 1 ratio means if you have 0.33 moles here, you form 0.33 moles of CO2. So N is 0.33 moles. R, they tell you to use 0.082. Temperature, they already gave you in Kelvin. 1 liter container. So again, 0.33 times 0.082 times 300 divided by 1. I guess 2 sig figs. Oh, well, it's multiple choice. Doesn't actually matter. Which value do you get closest to? 8.1. And when you plug it into your calculator, you actually get 8.118. But it's multiple choice, so you just pick the answer that's closest. So 4 is looking at ensuring that when you are plugging information into the ideal gas law, that you are plugging in moles of a gas to find the pressure. Now, if these both were gases, well, then you would have to find the pressure of each gas and add them together. But it's not, it's just one gas. Any questions on the do now? Trying to pull lots of different questions. We'll do more multiple types of questions tomorrow as well.
Yeah, so you said if there's more than one gas, can you use the partial pressure?
Yes, so let's say that calcium oxide, which it never will be, but let's say calcium oxide was a gas as well. And it said this solid decomposes completely into 2 different gases. Well, then you would say, okay, well, I would have 0.33 moles of calcium oxide, just still based on stoic, and 0.33 moles of CO2. So you have one of 2 ways that you can do it. You can solve for each individual partial pressure and add them up. Or just keep in mind if this is P total, this should be N total. So you can always just add up the moles and plug it in as well. Either way would work. You'd get the same thing either way. But you just have to keep in mind that if you have multiple gases, you have to take every gas into account. But it's only gases that affect the pressure of anything. Yep. Any other questions?